Okay, thank you very much to Professor Saya Negami for the interesting talk. So now we are welcoming Associate Professor Kenta Ozeki, who will talk
Nakamoto,
about,
Nakamoto.
yeah.
I'm sorry, the second one is Nakamoto, please. I'm very sorry.
Okay, so I'm sorry for, okay, so Professor Atsuhiro Nakamoto, are you connected with us? Can you hear
Yes.
our voice?
Yes, I'm
Okay.
Nakamoto.
Okay, good. Okay, so welcome Professor Atsuhiro in Bali, virtually.
Yes.
We are going to listen to your presentation now. So as written on the schedule, you are going to talk about flip distance of triangulation on surfaces, right?
Yes.
Okay, so
I will
Professor
share.
Atsuhiro, you may
Yes.
share your screen.
Yes. Sorry, can you see?
Yes.
So, thank you for the introduction. My name is Atsuhiro Nakamoto. Okay. I'd like to talk about flip distance of triangulation on surfaces. Okay. First of all, I would like to thank the organizer to invite this workshop on optimization using graphs. Okay. I really wanted to visit Bali, but now I'm in Japan. It is very pity. Okay. So I will start my talk. Okay. Is this presentation is correct? Okay.
Yeah, we can see that the title of the slide is Triangulation on Surfaces.
Okay, yes. Okay, yes. So a triangulation G on surface is a map of unraveled simple graph on the surface such that each face is bounded by a cycle of length 3. Okay, so this is an example of triangulation on the sphere, which is isomorphic to the octahedron.
Excuse me?
Yes.
I think that you have a long presentation mode.
Okay, so I should exchange display like this.
It
Is
seems
this
fine.
correct? Okay.
Yes, it looks fine.
Yes.
Thanks.
Okay, thank you. So yeah, this is another example of triangulation on the torus from this rectangle. Okay. So from this rectangle, we have a torus by identifying red segments and blue segments respectively. Then we get a torus, okay? This is a triangulation on the torus whose graph is K7, okay? So when we embed the graph on the sphere, then the number of vertices minus the number of edges plus the number of faces equals 2. We have, which is called Euler's formula, okay? And we substitute this relation for triangulation. 2 times the number of edges equals 3 times the number of faces. Okay, eliminating f from these two equations, we get this. Okay, the number of edges equals 3 times the number of vertices minus 6. Okay, this means if we fix the number of vertices in triangulation, then the number of edges is automatically determined. Okay. Moreover, by this relation, the number of faces is also automatically determined by V. Okay, please remember this. Okay. So for the torus, we have a similar fact, but today's talk, we concentrate only triangulation on the sphere, so we omit the detail for the torus. Okay. So I'd like to introduce elementary operation for triangulation called diagonal flip. Okay. So a diagonal flip, diagonal flip is to switch the diagonal to move it to another diagonal like this. Okay. But if the resulting graph is not simple, we don't apply this operation. Okay, this means we would like to keep the simpleness of graph always. Okay. And triangulation G and G prime are said to be equivalent and denoted by this symbol if they can be transformed into each other by diagonal flips. Okay. The flip distance, this terminology is appeared in my the title of the talk. Okay. The flip distance of G and G prime is the minimum number of diagonal flips needed to transform G and G prime, and denoted by this G prime. So we'd like to introduce a classical result called Wagner's theorem. Okay. Wagner's theorem states that any two triangulation G and G prime on the sphere with the same number of vertices are equivalent to each other. Okay, so these are two triangulation on the sphere with 6 vertices. So believing this theorem, they can be transformed into each other. Okay, we do. So we first, as we mentioned before, if we fix the number of vertices like this, then the number of edges and the number of faces are automatically determined. So if we assume this and this have the same number of vertices, then they also have the same number of edges and same number of faces like this. Okay, we have a demonstration like this. Okay, so we move this edge like this. Okay, move this edge like this. Okay, so moving the position of these 3 vertices by homeomorphism on the sphere, we get this. So those 2 triangulation can be transformed into each other. Okay. So Wagner's theorem has been generalized to non-spherical surfaces, and many YNU people contributed to such a topic. Okay. But today we concentrate only triangulation on the sphere and consider flip distance of them. Okay. Okay, we'd like to introduce Wagner's proof. Consider a triangulation on the sphere, and we focus on top vertex V. Okay, and we consider whether this edge can be flipped like this. Okay, if we can flip this edge, then we proceed. Okay, so suppose it is forbidden, then we have such an edge. Okay, in this case, if we flip this edge to here, then we have multiple edges. Okay. However, by planarity, in this case, we have such an edge. We don't have such edge, so we can flip like this. Okay, therefore, by So now we find that at least one of this edge and this edge are flippable. So repeating these procedures, we get this. Okay, so we can always decrease the degree of B. Okay, so we get this. Okay, repeating these procedures. Okay, and now we focus on this part and consider the degree of this. Okay, then we repeat as before. Then we get this, and we eventually have such a structure. Okay, we call this the standard form of spherical triangulation. So Wagner's method is as follows. Every triangulation can be transformed into the standard form by diagonal flips. Okay, so any two triangulations can be transformed into each other via the standard form. Okay, so this finishes the proof of Wagner's theorem. Okay, using Wagner's algorithm, let's estimate the flip distance of G and delta n. Okay, so from this to this, the leftmost one and the next one, okay, we had at most n-1 edge here, and in this triangulation, this vertex has degree 3. Okay, difference is n-4. So we needed at most n-4 from this one to this. Okay, so the next, now we have at most n-2 edge here, and here we have 3 edge here. So the difference is n-5. So repeating this summation, and we got this order n square. So Wagner's proof implicitly shows the flip distance of any two triangulation G and G prime on the sphere with n vertices is order n square. Okay, is it best possible? We'd like to consider this. Okay. So now we consider two triangulation which need many flips. Okay. So for this question, there exist two n-vertex triangulation G and G prime whose flip distance is at least 2n-15. Okay. We can prove this one very easily, so I'd like to mention it. And very recently, this 2n minus constant has been improved to this. Okay, but a little bit complicated, so we mention this one. Okay. Consider G, which is a triangulation with maximum degree 6. Okay, such a triangulation can be easily constructed. Okay, and another one is the standard form. Okay, so in G, every vertex of G has degree at most 6, but in G prime, there are two vertices with very large degree. Okay, this and this. Okay, this is a difference. And consider the flip distance of this G and G prime. Okay. And we consider effect of a single diagonal flip to a triangulation. Okay, in this case, the degree of U and the degree of B increased by 1 respectively. Okay, so let's consider the flip distance of G and G prime. Okay, okay. Since each vertex in G has a degree at most 6, okay, so these two vertices become this and this. We may suppose this, okay? So let's consider this. If this x, this x and y are not adjacent, then degree x and degree y might be increased simultaneously. Okay, but if degree x and degree y are increased simultaneously, then in the resulting graph, x and y are adjacent. Okay, and if x, y are adjacent, then we cannot add edge xy anymore. So at most one of degree x and degree y is increased by any single diagonal flip. Okay. Therefore, we have to increase the degree of x and degree y almost separately. So the flip distance of this g and this g prime is at least these numbers. Okay, so the flip distance is at least 2n minus constant. Okay, so so let's consider upper bound. We already know there are lower bound with the lower bound is linear. So now we mention the upper bound is also linear. Okay, so this is our result. Let G and G prime be n vertex triangulation on the sphere. Then the flip distance is at most 6n. Okay, so upper bound is 6n and lower bound and 2n. So yeah, we want to know the coefficient, real coefficient. Okay, so linear bound was first given by Komuro in 1997, but our result gives a much better explanation, and moreover, it is easily understood. So we'd like to mention this one. Okay. And after that, these people improved this 6n to 5.2n, and very recently, these people improved this 5.2n to 5n. Okay, I think this is currently the best bound. Okay, so but we'd like to introduce this one, this result. Okay. So the method is to use Hamiltonian triangulation. So our purpose is to prove if G and G prime are n vertex triangulation on the sphere, then the flip distance is at most 6n minus constant. Okay. So in order to prove this, we use this lemma. Okay. Let G and G prime be n vertex Hamiltonian triangulation on the sphere. Then the flip distance of G and G prime is at most 4n. Okay, if we compare this and this, so in this lemma, if we assume Hamiltonian triangulation, then the flip distance is decreased. Okay, from 6n to 4n. Okay, so we prove this. So let G be a triangulation on the sphere with a Hamilton cycle C, like this. Okay. Hamilton cycle is the cycle passing through each vertex exactly once. Okay. Then we can see that the interior and exterior of C are maximal outer plane graphs like this. Okay. So we have this. Okay, so our idea is to decompose Hamiltonian triangulation into two maximal outer plane graphs. Okay, so now G has a Hamilton cycle C, so G has two spanning maximal outer plane graphs H1 and H2 sharing C. Okay. And our idea is to apply a diagonal flip in H1 or H2. Okay. But we have to be careful to consider this edge. Okay. So, of course, this edge is flippable in H1 to be able to put this one here. Okay. However, the edge 2,4 already here, so flipping this edge is possible in H1. However, it is impossible in G because of edge collision of this and this. Okay, so we have to be careful. Okay, so we focus on this vertex. Okay, so H2 is also a maximal outer plane graph. So this has a vertex of degree 2. Okay, so we can find no inner edge incident to this. Okay, because this has a vertex of degree 2 in H2. Okay, therefore we can do this. Flipping this and flipping this and so on. Okay, so we can increase the vertex 1 like this. Okay, 1 by 1. Okay, so now we have this edge has at least the degree of this vertex has at least 3, and here we have the degree n-1 here. Okay, so the difference is at most n-1. So we needed at most n-1 flips from this to this. Okay, now our graph is obtained from this one and this one by pasting them along C. Okay, so now we transform this. Okay, and we focus on this part, this vertex. Okay, we have no inner edge incident to this vertex 2, so we can do that. Okay, flip this edge to here and flip this edge to here and so on. We can increase the vertex, the degree of vertex 2 to n-1 here. Okay, so we need at most n- constant flips. Therefore, no. Okay, now our graph is obtained from this one and this one by pasting them along C. Okay, what is the resulting graph? Okay. Our graph is as follows. Vertex 1 has degree n-1 and vertex 2 has degree n-1 and they are adjacent. Okay, so our graph is nothing but the standard form of spherical triangulation like this. Okay, therefore, if G is n-vertex Hamiltonian triangulation, then the flip distance of G and this one, the standard form, is at most 2n minus constant. This means for any two n-vertex triangulation G and G prime on the sphere, the flip distance is at most 4n minus constant. Okay. So, let's prove our main result. Okay. Let G and G prime be n-vertex triangulation, G and G prime. Okay. Suppose G can be transformed into a Hamiltonian one, and G prime is also transformed into G prime Hamiltonian one. Okay. By the lemma, okay, this Hamiltonian triangulation and Hamiltonian triangulation can be transformed into each other by at most 4n diagonal flips via the standard form. Okay, So we have to consider how can we transform G into a Hamiltonian triangulation. Okay. So for this purpose, we use this TAT result. Okay. Every four connected planar graph is Hamiltonian. Okay. So applying at most n-1 flips, we can prove G can be transformed into four connected one. Okay, we omit the proof, but so by using this extra diagonal flips, we get 6n diagonal flips are sufficient. Okay, this is a proof. Okay, we already mentioned someone improved this 6n to 5.2n, but they actually improved this n-1 flips to this many flips. Okay, by this improvement, they improved 6n to 5.2n. And yeah, it is best possible if we try to transform G into a four connected one. Okay, they insisted. Okay. Moreover, they improved this flip to this. Okay, but they gave up to transform G into four connected one. They didn't use this one, and they count the number of flips to transform G into just a Hamiltonian one. Okay, so by this improvement, they got this result, which is currently the best bound, I think. Okay, so I'd like to give conclusion for the spherical case. Okay. Wagner first proved that any two n-vertex triangulations, G and G prime on the sphere, are equivalent. And his algorithm suggests the flip distance is of order n square. Okay. We currently know the flip distance for any two triangulation G and G prime on the sphere at most 5n minus constant, but we can construct G and G prime with flip distance is at least this many diagonal flips. Okay, so we want to know the exact coefficient. Okay, I think it is difficult. If we establish an argument without the standard form, we will be able to get a better bound for the flip distance of G and G prime. Okay. So that's all. Thank you very much.
Okay. Thank you very much to Professor Atsuhiro Nakamoto for a very nice talk on the flip distance of triangulation on surfaces. Okay, before we go to the third speaker, I'd like to tell the participants who want to ask questions. So for those who join us on the Zoom meeting, you can start to write your question via the chat room. Please tell your name and your affiliation and your question, and then I will help to read the question on the question and answer session.